Our final topic from this unit is our topic from Chapter 8, which is torque. And torque is the quantity that measures the ability of a force to rotate an object around some axis. The lever arm is what we're going to call the distance from the axis of rotation to the point where the force is applied. And the only force that will cause something to rotate is the force that's applied perpendicular to the lever arm. The symbol for torque is the Greek letter tau, and the equation for torque is the lever arm, which we're going to symbolize by R, times the force perpendicular to the lever arm. So that's going to be the force times the sine of the angle. And we'll see how that works when we take a look at a couple of problems. Torque can cause something to rotate clockwise. It can cause something to rotate counterclockwise. And so it turns out that depending on which way something rotates, we give it a particular sign, plus or minus. So when I have a plus for torque, I have counterclockwise. So it's going to rotate around that way. If I have torque that is negative, then I have clockwise. Unfortunately, this relies on the fact that people know what an analog clock is and which way the hands rotate on a clock. For those of you that are used to digital clocks, it may not be that helpful. So how would I do a torque problem? Force is applied to the end of a lever. Here is our force of 15 newtons. We want the component of that force that is perpendicular at that point. And we get that by taking the sine of our 40-degree angle. So we have a force, 15 newtons applied at a 40-degree angle. It's going to cause the lever arm, this bar here, to rotate that direction, counterclockwise. So it's going to create a positive torque. What we need to do if we want to balance it, because we want rotational equilibrium, that means no motion, or we have a balanced situation. So we need to find the torque that's being created, and then we need to apply a torque in the opposite direction to prevent that rotation. If the force we apply is at this position, it needs to balance that force. So we can easily find that. So right now 14.5 newtons is being applied to cause the object to rotate in a counterclockwise motion. So we need to apply 14.5 newtons, but in the opposite direction. So we'll make it negative 14.5 newtons. It's helpful many times to draw pictures when you're doing these problems. If we look at number 2, we have two kids sitting on either ends of a seesaw, and we want to figure out where do we put the pivot point so that they will be balanced. They will not be tipping up or down. So here is our lever arm. It's 2 meters long. And the kids are at each end, so we have 40 kilograms at one end, and we have 30 kilograms at the other end. And we want the rotational torque by the 40 kilogram kid to balance the rotational torque for the 30 kilogram kid. So we're going to say 40 kilograms times 9.81 times x. X equals the lever arm. And that's going to equal 30 kilograms times 9.81. And then we're going to say 2 minus x here. 2 minus x, because the full lever is 2 meters. And we said x is the distance from the end to where the pivot goes on one side. So what we have to do is solve for x. We find that x is equal to 0.857. And so from the 40 kilogram end in, not quite all the way, because the heavier kid is going to create a bigger torque due to its force, we have 0.857 meters. And the lighter child will sit 1.143 meters away from the pivot point. All right, same setup. So we have 40 here, 30 here, we have 0.857 meters there. Now we're putting a 23 kilogram child 0.2 meters from the 40 kilogram child. So this new child is sitting on the left-hand side and sitting in 0.2 meters. So right here is my new child. So before this child sat down, the system was balanced. So I really just need to figure out what is the torque created by this new child, because that's what's upsetting and then balancing my system. So I'm going to take my child's mass times g times the distance this child is from the pivot point, which is 0.2 meters less than 0.857, so 0.657 meters. And I get 148.2 Newton meters. Newton meters, force times distance, is our unit for torque. And it is not joules because the force is perpendicular to the distance. We're not doing work, we're causing rotation. So torque units are Newton meters. All right, we're adding one more child. And we want to place this child to recreate equilibrium. So this 33 kilogram child needs to balance the torque we found here, 148.2. So we can use that and work backward. So the torque we have to create is 148.2 Newton meters. That's going to equal this new child's mass. So if we solve for x, this is the position the child is, 0.458, and this is from the pivot point, and it's on the same side as the lighter child, as the 30 kilogram child. All right, give me a lever long enough and I will move the earth. Some famous old guy said that. Let's say that you weigh 735 newtons, and we have the weight of the earth, 5.87 times 10 to the 25th newtons. We have a mass of you and mass of the earth also provided. You wanted to lift the earth with a lever arm, and the lever arm is 1 centimeter on the earth side, and you're going to stand on the other side. And the question here is, how long does your side of the lever arm have to be? Well, we know the weight of the earth and we know its lever arm. So we can take force perpendicular times distance, so 5.87 times 10 to the 25th newtons times 0.01 meters. Your weight is only 735 newtons. And how long does your lever arm have to be? Pretty long, it turns out. 7.99 times 10 to the 20 meters. That's pretty long. Now, with a problem like that, we actually had to make some assumptions, and actually those assumptions are impossible. So, some impossible assumptions that we had to make. What were they? Well, you have a lever. A lever needs a pivot point. If you're trying to move the earth, the pivot point needs to be fixed and not moving. To what would you fix the pivot point in space so that you could use a lever? That's one assumption that you're making that is never going to happen. The next assumption that you're going to make is the lever arm on the earth side is only 1 centimeter. Well, that's not going to work because the earth is a lot larger in volume than 1 centimeter. So there's no way that you could have a lever arm on the earth side of just 1 centimeter and attempt to move it. So there are actually two impossible assumptions that you have to make to solve this problem. And the last one, who actually said this? So we need a person that came up with it. And then second of all, is this exactly what this person said? If not, what did he really say? And so that's some research for you to do, and it would be good for you to bring that answer to class when we discuss this vodcast. This last page is really just a summary of all the formulas that we've talked about with this unit, and you have them on the note sheet so you can use them as your handy reference as you're going through and working the problems on this chapter.